this video, we'll talk through the oxidizing reducing agents topic from Higher Chemistry Unit 1. By the end of this video, you should be able to explain what oxidizing reducing agents are, give examples of both oxidizing and reducing agents, balance ion-electron equations, combine those ion-electron equations to produce redox equations, then work with redox equations to identify oxidizing and reducing agents within them. Start off with a recap of National 5's oxidation and reduction. Oil rig is a way that lots of teachers talk about reduction and oxidation, where oxidation is the loss of electrons and reduction is the gain of electrons. If both of these things happen in the same reaction, we have a redox reaction. Here we've got two chemicals, one of which is losing electrons, one of which is gaining electrons. The aluminium is losing electrons because at the end the electrons have moved away from the aluminium and we now have a positive charge in the aluminium ion. For the copper, we have the electrons on the left hand side, they are gaining electrons, therefore that's going to be a reduction. If we know we're talking about redox, one of the half equations will be oxidation, the other one is going to be a reduction. We can also use the electrochemical series. This one is the higher version, which is slightly different from the National 5 one, works in a very similar way. These equations are all reductions, as it says at the top of the page. If your equation looks like this, that means you've got a reduction. So electrons on the left-hand side, we have a reduction. If they were on the right-hand side, we would have an oxidation. A lot of the reactions that you would have looked at in National 5 involved electrochemical cells, where you have two metals connected by a wire in an electrolyte, which allows the electricity to flow. Electrons will flow from the substance that was higher up in the electrochemical series down to the one that's lower down in the electrochemical series. In this case, we've got aluminium and copper. Aluminium is higher up, therefore it will lose its electrons to copper. That's why aluminium is being oxidized and copper in this case is being reduced. Before we can combine these two equations, we have to make sure we have the same number of electrons in both of them. We do not. We're going to take the aluminium equation and we're going to times it by 2. The copper equation will be times by 3 to allow 6 electrons in both equations. We then take everything that was on the left-hand sides of each equation, put them together, do the same on the right-hand side. We're looking for anything that we can cancel out. Both sides have 6 electrons, so we can chop them out to leave our redox equation as shown. Redox equations will not have any electrons. The electrons have to cancel out before we can combine them together. The new part, as we're moving on to our higher, we're talking about oxidizing and reducing agents. The way this was explained to me was thinking about travel agents. Travel agents' job is to help people go on holiday. They themselves don't go on the holiday that they are organising. It's similar with oxidizing and reducing agents. An oxidizing agent will cause another reagent to lose electrons. It causes oxidation to happen. The oxidizing agent itself will gain the electrons from the other chemical. Therefore, it itself will be reduced. A reducing agent causes things to gain electrons, so it causes reductions to happen, and it itself will be oxidized, it will lose electrons. Electronegativities, which was spoken about in the periodicity topic, this can help predict whether an element is likely to be an oxidizing agent or a reducing agent. If an element has a high electronegativity, it's going to be able to pull the electrons away from the other species. Therefore, it will tend to act as an oxidizing agent, something that helps cause oxidation in something else. Things with the highest electronegativity are things like the halogens, so something like fluorine or chlorine, are really strong oxidizing agents. You also need to be aware of non-element oxidizing agents such as dichromate and permanganate. Things with a low electronegativity will tend to act as a reducing agent. Something like the alkali metals, which have a very low electronegativity, are good examples of this. Carbon monoxide is an example of a non-elemental reducing agent. We can again use the electrochemical series to help us with this. So here, if we look down at the bottom left, we have fluorine, which is a really strong oxidizing agent, whereas lithium up at the top right would be a really good reducing agent. Now we're going to look at a couple of questions based on the things that we've just spoke about. Here we'll be given a reaction that takes place in a carbon monoxide sensor. We're asked if this is an example of reduction, redox, oxidation, or hydration. The fact that there are electrons shown in this equation means it cannot be redox. In a redox equation, the electrons have cancelled out one another. A hydration reaction involves a carbon-to-carbon double bond being broken and water being added across it, which is not what we have here. That leaves reduction or oxidation. If we look at where the electrons are placed, this is showing that electrons are being lost. Therefore, this is going to be oxidation. What you could also do, if it's going to make life easier, is look on page number 13. These are all reductions, and the electrons are on the left-hand side, but our example has the electrons on the right-hand side. Therefore, it is an oxidation reaction. In this one, we're asked about which of the following elements is the strongest reducing agent. This means it's really good at helping other things to gain electrons. What we're looking for, therefore, is something that has a low electronegativity. And in this case, the chemical which has the lowest electronegativity will be lithium. It's at the top right-hand side of the electrochemical series. At higher, we'll get a lot of group ions or compounds or molecules involved in our reductions and our oxidations. Here are some of the examples. You can find these in your data booklet. Things like hydroxide, nitrate, and sulfate you should be familiar with from previous work. When we're balancing these ion-electron equations, we need to write down what we know at first. We're going to balance oxygens by adding water. We're going to balance hydrogen by adding hydrogen ions. And then finally, we'll balance the charges by adding electrons. And we'll go through a few examples just now. Here, we've been asked about sulfur dioxide being oxidized to sulfate ions. Therefore, we've got SO2 going into SO4 2-. First step is balance the oxygens by adding water. At the moment, we have 2 oxygens on the left, 4 oxygens on the right. If we add 2 waters to the left-hand side, we've got our oxygens now equal on both sides. We've now gotten the issue of hydrogen. To balance the hydrogen atoms, we're going to add hydrogen ions to the opposite side. So in this case, we need 4 of them because there's 2 waters. So 4H plus gets put on the right-hand side. We then need to look at the charges to make sure that we've got an equal charge in total on both sides. At the moment, we have 0 charge on the left-hand side, but we've got 2 positive on the right-hand side. So we have SO4 2-, and then we've got 4H pluses. So 4 positive, 2 negative, overall it's 2 positive. We are only at this point allowed to add electrons, and if we add 2 electrons to the right-hand side, we've now got 0 charge on both sides. So you have to try and get both charges to be the same. For this question, we're asked about a reaction where periodate ions are reduced to iodate ions. First off, look and see if we have the correct number of iodines, which we do. We need to fix the oxygen situation by adding water to the other side. So we want 1 water on the right-hand side. That causes an issue with hydrogen, which we can fix by adding 2H plus on the left-hand side. We look at the charges that we've got on each side. If we put 2 electrons beside the 2H pluses, that balances out our charge and completes our ion-electron equation. A lot of the questions you can find help for within page 13. It might not always have the exact same chemicals, but the layout of them will be very similar to what you're asked about. So the previous question is not here, but we can see that the hydrogens and the electrons are on the same side. And that's the same in other examples that we've got as well. So you can often refer back to page 13 just to help get it straight in your mind what it is you need to do to successfully balance the ion-electron equation. In this one, we're given options for what the possible numbers could be. Sometimes this can be a bit more tricky because if you're led down the wrong pathway, that might look like you're actually doing the right thing because it matches one of these options. I'm just going to approach it in exactly the same way. First thing we need to do is look at the iodines in this case. Do we have the same number of iodines on each side? We do not. So we're going to have to double up our left-hand side, like so. We can then look at our oxygen. Now, because I've put a 2 in front of the IO3, I need 6 waters this time. And that's one of the examples where people can go a little bit wrong. Because I've added 6 waters, I need 12 hydrogen ions, so 12 H pluses, like so. We then look at our charges. We've got 2 negative and 12 plus on the left-hand side, and we've got 0 on the right-hand side. What we want to do then is we want to eliminate those extra 10 plus, 2 minus 12 plus, 10 plus. So I'm going to add 10 electrons to that left-hand side, and that's going to make it 0 on both sides, successfully completing my ion electron equation. We're asked about H plus and H2O, therefore it's 12 and 6, which gives us the answer of D. You may be asked to join together oxidation and reduction ion electron equations to make those redox equations. We still need to look at the number of electrons in both before we combine them together. If you're given these two ion electron equations, we can see we do not have the same number of electrons in each in a moment. If we take the iron one and times it by 5, that will then get 5 electrons on both sides. We can then cancel out the electrons, and everything on the left-hand side of both equations goes together, and then the things that are on the right-hand side of the equations go together to give us our redox equation. Here's an example of an exam question asking us to, again, do that very same thing. In this case, we do have the same number of electrons in both. Makes our life a little bit easier. I'm going to write down everything on the left-hand side together, everything on the right-hand side together. What we can then do is start to chop away anything that appears on both sides. There are 4 electrons on both sides. Get rid of them. There are 4 hydrogen ions on both sides. We can get rid of them. We have 1 water on the left and 2 waters on the right. So we can cancel that down to give us our correct answer, where we've got O2 plus CH3CH2OH plus water, and we have CH3COOH. So we have our ethanol reacting with oxygen to make water and our ethanoic acid. You could be asked to work backwards from an already combined redox equation, and you might be asked to separate them into an oxidation and reduction, or asked about oxidizing and reducing agents. In this example, I'll do all of those things, and I'll show you a couple of examples of what they specifically want in exam questions. Here is my example where I have chromium ions, some water, some chlorine, we've got dichromate, hydrogen ions, and chloride ions. We want to try and separate these out into 2 parts and look at what things go together. For me personally, the chlorine is the easiest part to start with. What you'll be able to see is that we have 3 Cl2, so 6 chlorines in total, and on the right hand side we have 6 Cl minus, again 6 chlorines. Once we take this out, it's missing electrons. We need to fill in the electrons to work out what's happening. We have a negative charge on the right hand side. To balance that out, I need 6 electrons on the left hand side. What we then have is the rest of the stuff. Because I put 6 electrons in the chlorine one on the left hand side, this means that in the other half equation, you've got to have 6 electrons on the other side, like so. We can then see that our charges match up and it's working out balanced as we wanted it to. We have our reduction equation here. It matches the data booklet, or it's gaining electrons. The other one has to be oxidation in that case. If I've done ever separating correctly, we get 1 reduction and 1 oxidation. Again, we could check that bottom one. It's not in the same order as the data booklet, therefore it's an oxidation. The chemical involved in the reduction reaction is our oxidizing agent. The chemical involved in our oxidation is our reducing agent. Oftentimes you'll be asked to talk about one of those 4 things. This is my process to make sure I know about all the parts of it to make sure I can answer my question correctly. In this question, we are given a redox equation and we are asked to give them the ion electron equation for the reaction of the oxidizing agent in this reaction. Again, I'm looking at what parts go together, which I've got here. I can then put my electrons in the correct place for the iodine one. So iodine has to be gaining electrons, therefore acting as my oxidizing agent. If we take the sulfur part, the thiosulfate, we can do a similar thing to get our second half equation. So our thiosulfate is being oxidized and it's acting as a reducing agent. Now our question specifically wants the oxidizing agent, which means the iodine part is the part that we write down as our answer to pick up the mark. In this question, we're working off of a description rather than a full equation with showing charges and things like that. We're going to look at the 2 different metals in here, so the silver and the aluminium, because they're going from being in a compound to being separated, and the aluminium was separate and now it's joined up with our sulfur. In this example, the silver is being reduced, which means it's acting as an oxidizing agent. We're going from silver ions to silver solid. Our aluminium is going to be losing electrons, so it's going to be oxidized. It's going to be acting as a reducing agent. Our sulfide is not changed. It's joined up with something at the start, and it's joined up with something at the end. And in each case, it's got a valency of 2. So you can work that through about what charges things have. Sulfide is a spectator ion in this case. Looking at the answers that we can select from, the only one that's correct is that aluminium is a reducing agent because it's helping other things to gain electrons, and it itself is losing electrons because it is being oxidized. Hopefully now at the end of this video, you're able to explain what oxidizing and reducing agents are, give some examples of oxidizing and reducing agents using the data booklet as necessary. You're able to balance the more complex ion-electron equations that are typical at higher level. You're also able to take a reduction and oxidation reaction and combine them to produce a redox equation. And then when you're given a redox equation, be able to pick out oxidizing and reducing agents within those. Thank you for watching. Goodbye.